All right. Last 30 questions? All right. Let me go over something with you. Please sit down. Guys, all right. Knock it up. I want to go through a couple of things that are real important with Fourier transforms. I got through the actual pulse function when it went to the transformer, but I haven't gone through the triangle. I want to make sure everybody follows me on this one. He doesn't do this very well, in my opinion. It's a pretty good book, but you know everything has areas of lapse, and this is his area of lapse. And some of these special functions that you need. Remember last time I said it. Is there a trash can in here? Oh, that's trash. Last time I said that if we have a pulse function, if this is t, and we have something where this is minus tau over 2, this is tau over 2, at a height of 1, we refer to that as the pulse function of tau, or rect of t over tau. Tau being the width, it's centered at 0 though. All right, now that's the standard function. We proved last time that this had a Fourier transform of tau here times the sinc of omega tau over 2. Y'all remember that, class? And the sinc function is an important one to know. You have to know this one. I'll just put it over here and hopefully you can refer to it. The sinc function, SINC of x, is simply defined as sine of x over x. And it looks like this, basically. This would be sinc of x versus x. That would be pi minus pi, 2 pi minus 2 pi, and so forth. So it's a damp sinusoid, basically. Now, the next function we're going to do, and this is an important one, but we're going to use properties to get at it. We want to find the transform of this function. And it just does this, where this is going to have a height of 1. This is called a triangle function. The symbol for this function is this. And you all remember that from before when we did convolution, the triangle function? How many do? The definition of this is really equal to 1 minus 2 times magnitude of t over tau times the pulse function tau of t. That's its definition, its mathematical definition. This is what it looks like. And this is versus t. With me, everyone? Now, we need the Fourier transform of that. In the book, where you saw a lot of these things where he had things that could be assembled by adding this to this. Remember that? You saw a lot of things that could do that. Or subtracting this from this, or some form like that. And so you have to have these two transforms, you have to have a working knowledge of it. So to get the transform of this right here, what I'm going to do is say, if I have a triangle function and I want the actual transform of it. So I've got a triangle function. And I want the transform of it here. I'm going to call this transform just x of omega. Are you with me? I don't know what it is yet. I'm calling it. Now I'm going to use a property. And I can take one look at that and I can say, I know if I take a derivative of this, I will get 2 pulse functions. Won't that, class? How many see that? A derivative would cause, and each one of those pulse functions, I know the Fourier transform of. But they would be time shifted. Are you with me? Please watch me. So if I take a derivative of this function, a derivative with respect to t of the triangle function of t, now what do I get? Well, I get something that's going to start at minus tau over 2 and come up to what height? Well, what's the rise over run? It rises 1, right? The run is tau over 2, so it would be 2 over tau, wouldn't it, class? So here, this would have a height of 2 over tau. But now what happens from here to here? Same magnitude, right? Only it's negative, correct? So now I get this. And this would be minus tau over 2. And that would be the derivative of that, wouldn't it, class?
Isn't that 2 over tau? Yeah.
This should be, sorry. This point would be tau over 2. and this would be 2 over tau. Only would be negative. I'm sorry. You're absolutely right. Thank you. Are you with me, class? Now, what is this really? How would I mathematically define this function? Listen up. I can mathematically define that as what? Wouldn't it be a pulse function, right? And the height is 2 over tau, so it'd be 2 over tau. This would be this part. It's a pulse function. The pulse function has a width here of tau over 2, right? And it's centered at what? T plus tau over what? 4. Take a look at that. That's the first part right here. Make sure you see how that is defined and you can agree with me. How many agree? You good? What's wrong, sir?
Is the magnitude T over tau?
2 over tau.
2 over tau.
Yeah, it starts at minus tau over 2, right? This is just the slope of this, right? The slope would be rise is 1, the run is tau over 2, right? So, it'd be, are you with me? All right, now what happens after that? I subtract then 2 over tau, right? Times a pulse function of tau over 2, and it would be t minus tau over 4. Does everybody see that? Are you with me? Please take a careful look. Make sure you convince yourself this is correct. You're going to be expected to do this kind of stuff. Everybody with me?
Okay, so it's just two pulse functions that you shifted. Okay.
That's right. Everybody got that? Now, when you take a look at this, and if I want the Fourier transform of this, right? We're going to get it in a second, but I'm going to make a point. If this is the transform I want, and I took a derivative of this function of t to get it, you know that's really equal to the property j omega, right? Times x of omega, right? Because if this went to x of omega, then the derivative in time of this function would be j omega times x of omega in the Fourier domain. How many understand that? That's a basic property you have to know, right? Yes, sir.
Can you repeat that? I'm sorry.
Sure. If you take a time derivative of any function, I mean, it assumes, you know, x of t goes to x of omega, right? Then if you take dx of t, and you want to know what the Fourier transform is, it's just j omega times x of omega. How many remember that property from last time?
And this is
The property that's like it is the Laplace transform property that what? Dx dt goes to s, x of s, minus x of 0. But because this starts at minus infinity, you don't have that problem with x of 0, t equals 0. Understand, class? Who else was asking? Was somebody else asking a question?
I was asking about initial conditions, but
You don't need initial conditions here. They don't exist for these kind of things. This is Fourier. They go from minus, the span is minus infinity to plus infinity. You don't have to ever worry about it. Are we good on this, class? Everybody? Now, look, let's do this transform. Work with me here. What is the transform? Well, the transform of this part, right, that's a pulse function, isn't it, class? So the transform of a pulse function, I didn't, yeah, I put it right here. That's the transform of a pulse function, right? Well, this pulse function has a weight in front of it, or a coefficient of 2 over tau. So I know, right off the bat, I'm going to put 2 over tau in front of everything. I know that that 2 over tau appears in both of these. Correct, class? Follow me? Now, the actual Fourier transform of a pulse function of tau over 2 of t is just what? Let me do it this way. If I just want to know the pulse function, or I mean the Fourier transform, isn't that simply tau over 2, right? Times what? The sinc, right, of omega, and then, not tau, but tau over 2 divided by 2, or 4. Agreed, class? Are you with me? Because the tau there represents, in which the omega tau over 2, that tau represents the actual width here, which is tau over 2. Understand, everybody? Give me a show of hands if you do. Please be very attentive here. Everybody see that? Now, next, if that's the case, what happens if I take this and I get p of tau over 2 delayed by t minus tau over 4? What does that delay do, class? It's going to bring an exponential out in the Fourier domain, e to the minus j omega times that delay. So now this would be tau over 2 times the sinc function, right, of omega tau over 4 times e to the minus j omega tau over 4. Agree, class? Let that sink in. How many see this right here? I want to get through this before I start working problems. Very important you see this. So now I can do this one. The derivative here, well, the first part goes to what? There's the 2 over tau is going to be in front of both of these. Then I have the transform of that right, oh sorry, that's a plus, this is actually a minus here, but I'll put it up there. That's going to be what? The sinc, right, of omega tau over 4, right? And then it's going to be, since it's the plus, it's going to be e to the j omega tau over 4. Then there's the minus sign. Now we do the Fourier transform of this part, right? The 2 over tau's out in front. And that transform is going to be sinc of omega tau over 4 times e to the minus j omega tau over 4. How many see what I've done so far? Right. I'm applying you all see it? Give me a show of hands, do you or not? If you don't see it, ask a question, because I don't know what you don't know. Yes, sir.
Would you need to multiply the front by tau over 2 for both of those?
Well, I've got the 2 over tau that's in front of both of these, right?
Right, but for the
And
pulse function,
this actually, I'm
So it
glad you
cancels out
said
with
that.
that?
I'm so glad you said that. This should have the tau over 2, my bad on that one. So this should be tau over 2, and this should be, tau over 2 here. And the upshot is what I was going to get at. Thank you very much. But what do you see happening there? Just take one look at that. What do you notice about 2 over tau times tau over 2? 1. Yeah, that's right. You can erase that. Thank you very much for catching me on that error. So this is the sinc of that. Now the next thing I'm going to do is simple. I'm going to factor out the sinc of omega tau over 4. It appears in both. Then when I do this, you see it becomes what? The sinc of omega tau over 4, and then I get this, e to the j omega tau over 4 minus e to the minus j omega tau over 4. Want to take a guess at what I do after that? Say it again. Say it louder.
Transform the e to the j omega tau over 4 stuff into zinc. Sine.
Isn't that the very definition right here of what? 2j times the sine of omega tau over 4? How many see that right there? Sure, from Euler's, right? In case you don't remember, Euler's said what? The sine of theta was e to the j theta minus e to the minus j theta over 2j. So if you multiply this by 2j, you have the difference in the exponentials right there. So I can say that this becomes simply 2j times the sine or times the sinc, pardon me, the sinc of sinc omega tau over 4, and then it's going to be times the sine of omega tau over 4. Are you with me, class? All right, how many see this? Now that right there is the Fourier transform of the derivative of that. Understand? But we don't want the Fourier transform of the derivative, we want the Fourier transform of that. So we have to divide what? This answer by j omega. Don't we, class? How many see this? If this is equal to j omega, x of omega, and I want x of omega, I divide that by j omega. I'm going to do it right here if you don't mind. Okay, class? Let me just do it right here. And if I divide both sides by j first, give me that. If I divide both sides by j, I get this, don't I? Agree? And then if I divide it by omega, I get this. Agree? Now, I need a 4 here, don't I? I mean, I want to get the same argument here as here so I can get a sink. Follow me, class? So here's what I'll do. I'm going to divide top and bottom by 4. It makes that what? 1/2, correct, class? And then I'm going to multiply top and bottom by tau. Do you all see why I'm doing what I'm doing? So when I do that, now I have this. Now why did I do that? Because what is this right here?
Sink of omega tau.
That's exactly right. It's just that, isn't it? It's sink of omega tau over 4. How many see this? And really what you can say is, therefore, the transform x of omega is actually, which is the transform of the triangle waveform, is tau over 2 times the sink squared, sink squared of omega tau over 4. So instead of, the pulse was what? Tau times the sink of omega tau over 2. The actual triangle is tau over 2 divided by, or times the sink squared of omega tau over 4. Understand? And this is one we're going to use all the time. You have to be real familiar with it. So that's how you get that one. Now, as far as an application, I gave you several Fourier transform problems to do. They were relatively simple, but the book chose not to do them by using properties, but by brute force integration. I may notice that, which is stupid. You're not taught properties, so you don't use it. Anyway, he just did it to make a point, really. How do you actually get that? If you wanted to brute force it, go ahead and do it. Knock yourself out, but properties make it a lot easier. I want to do some of these. All those properties are so important, and you have to work with them to really understand them and more or less retain them. The properties are very similar. Most of them are almost identical, just we're changing S to J omega to the properties of the Laplace transform. There's a few different ones, right? The big one that I talked about was duality. That's the super powerful one that we'll be using all the time. But now I want to go through some of them. There was, I'm gonna just pick a couple of problems, all right? I mean, does anybody have a problem they want to see done? I'll be happy to do it. Yeah. Did you say?
No, I'm cool.
All right, give me isn't the first problem just like a triangle?
Yeah.
Isn't it like, tell me if I'm right, isn't it this?
Yeah, that's all.
All right, what's the height on this one?
A.
What's that?
5.
5. All right, well, let's leave it as A, we'll put it in A's 5 at the end, all right? And where does it stop? The T? All right, now I take a look at this, right? A couple of ways to do this. Well, I'm going to do it the way that's most obvious. Y'all agree a derivative of that would give me a pulse, right? With a delta function. Do y'all agree with that? How many see that right there? So I'm going to call this my x of t. And what I want, that x of t, I know is going to go to some x of omega that I don't know. I don't know that. But the next step I'm going to do is take a derivative of this with respect to t. So when I take a derivative of x with respect to t, now I get something with a height equal to a over cap t. Do you agree with me, everyone? And it stays there until what?
Until t.
And then what happens? I got an impulse then, right? It goes from instantly from a to 0, or an impulse function now is required. So I come here and I have an impulse. And the impulse has a height of a negative a, and it's delta t minus cap t. Is that right, class? How many see that here? So this is made up, the derivative is made up of a pulse centered at t over 2, this is t, plus an impulse. Do you agree with me, class? I'll write it down. This dx dt is technically equal to what? It's a pulse, a over t is the actual scale in front of it. Then it's a pulse, the width of the pulse is cap t, and it's centered at t minus cap t over 2. And then add to that, or subtract rather, minus a delta of t minus cap t. Isn't that the mathematical definition of that derivative? Please take a shot and look at that. Y'all see it? Can y'all see it in the back there? Guys?
It's just because like
If you go from A, right, to 0 instantly, that's a delta function. All right, because if you integrate a delta function, you get a u at t or a constant. All right. So what happens now? My dx dt here becomes what? Well, what's the Fourier transform of that? Y'all agree the a over t is going to be out in front, class? All right, what about this one? Well, what is it? That's going to have tau, right, times a sinc, right, of omega cap t over 2, correct? And what about this e to the minus j tau, or t over 2? E to the minus j omega, right, times t over 2. That's the first part, isn't it, class? And I'm going to block that. What about the second part here? The weight is a, right, minus a, so you put a minus a down, don't you, class? What about a delta function? Delta of t goes to 1. Delta of t minus cap t goes to? Right, good. Times e to the minus j omega cap t over, just cap t, pardon, just cap t. Correct, class?
Yeah.
All right, now that is the derivative, right? Or it's equal to j omega times x of omega. Isn't it, class? Isn't that right? Right? How many see this? Realize the property. If x of t goes to x of omega, then dx of t goes to j omega x of omega, correct? Now I'm going to get the x of omega by simply taking the Fourier transform of the derivative and dividing it by j omega. I think you can see my madness now, right? Everybody? What I'm doing? So if I divide that by j omega, and I'm going to do it right here, as such, not even bother with that. Now I have my x of omega. That is a perfectly legitimate answer. But here's the thing. Usually they would like to turn this into something understandable, like a sinc function. You all see that? Now I've got e to the minus j omega t over 2 here, and I have e to the minus j, or e to the minus j omega t here. Maybe I can't do it. I was thinking I could get away with it, but, and there's probably, if I fussed with this enough, I probably could. I'm not even going to bother. This is legitimate. This is the Fourier transform of that. Understand, class? And that way I don't have to do the integration by parts with t times e to the minus j omega t dt. Even though it's doable that way, it's, in my opinion, this is a better answer. It's more obvious. It's quicker. Another problem. How many understand this right now? You've got to stay on point here. You have to be observant. This is a class you can easily fail if you aren't that way. It requires a lot of attention to detail. You got to be smart to start with, and you have to have a very good analytic mind, but you have to be attentive. This isn't something you're just going to skip through. So that's really the application of one of the properties, the derivative property. All right, now, a couple others. I'm going to show you, let's see, what's the next one?
The next one's just a triangle function.
Just the triangle?
Yeah.
Forget it. We just did the triangle.
The next one's a sawtooth followed by a negative sawtooth.
Oh, that one. Here, let me show you a couple tricks before we do that one. All right, got a question for everybody. Suppose this is on a quiz, and it looks like this. I'm trying to make that vertical. I'm not doing a good job. I'm just going to let the height 1 here. And this is my x of t. And I want my x of omega. Capital X of omega. How would I get that? Based on what you know. Think of the building block approach. Go ahead.
Derivative.
Why a derivative?
So you get the square pulses.
You don't need a derivative. You could do a derivative, but isn't that just the sum of a pulse minus a triangle? How many see that right there? I can say that this x of t is nothing more than a pulse of width tau, right? Minus a triangle, right? Of width tau, isn't it? First convince yourself of that. How many see that? This is the way you think as engineers. Use a building block approach. If you can assemble what you're looking at with the basic functions, do so, because you know the transform relationships. Yeah, you can't take a derivative. If you want to, you can. The problem with that is I get an impulse here, then I get another square here and another square. I got 4 things to worry about. You don't need to do that. Those are 2. Do we know the transform of this
Yeah.
and this?
Yes.
We're done. Understand? Now that's a building block approach, and this is very important. Now, if you got something like this, I'm going to ask, if you want to do this, we can. I'm going to put this up here, I'm going to ask some questions. I'm going to keep on perturbing this. So now, if I take that, I know this is really going to be what? Tau times the sinc of omega tau over 2, right? Minus tau over 2 times the sinc squared of omega tau over 4. Isn't that right? Based on what we've just done. How many understand that? You're with me, class? Right? It's very straightforward, very obvious, but you've got to be attentive here. There's nothing magically hidden and stuff. I'm not doing some crazy math. It's very obvious. Now, what?
I said it isn't crazy math, but
It's not crazy math. Come on, you add 2 numbers. They're just 2 functional forms. That's not crazy. I'll come to crazy later.
Can you explain how you really just got the pulse function minus the?
All right, think of it this way. If this is a pulse, right, as such, what do you need to do to make it that? Don't you just subtract the triangle from it? Right? That's it. That's the reason I subtracted the triangle. If I added the triangle, what would happen? Then it would do this. Then I would have a box with a roof. Understand, class? How many do? This is the way you always approach these things. Now, after that, all right. Now, yes, sir.
For the pulse, isn't it tau over 2, not tau? For the
This is tau over 2, and this is omega tau over 4.
that's correct.
Just check it. Trust me on this one, all right? Now, keeping going. What happens if I ask for the transform of this? This is 0, and now I have this. Where this is going to be t, this is t over 2, height of 1. What do we do with this?
Isn't it the same function times e to the negative j?
Exactly. He's taking the same function. Let me put tau here, not t. All right. That way it'll be the same stuff. And all we're doing is what? Shifting it by tau over 2. So you multiply it by e to the minus j omega tau over 2. How many see this? All right. What if I asked you to do this one? I'm perturbing it on purpose this way. Here's the function. Now what do I do? Minus 1.
I guess negative.
Multiply by minus sign. You get the idea? And this is the way you do all these things. Look at the basic building blocks that it's composed of, knowing the transform pair relationship, assemble them, and then do any kind of phase shifting you need. Yes, sir.
So I understand, but the one because the second one.
This one.
Yeah, I understand that's what's said. But you said multiply by what again?
You have to do a phase shift. This would be multiplied by e to the minus j omega tau over 2 because it was shifted that far. Remember, if you have a time delay, which we're delaying in time, isn't that right? If you time delay turns into phase and frequency. Just look at the property. How many understand that, class? All right, now you can see how all of a sudden wheels start turning in your head. You can see the patterns where all you're doing is recognizing certain patterns and bang, you've got it off, you've got these. Now, you asked me about, what was the other one you were saying?
It's a sawtooth, so I can bring it up there.
No, stay there.
It's a sawtooth followed by a gap and then an inverse negative sawtooth.
All right. I'm going to make one stipulation before I start this one. Give me this, guys. From before, we had this, where this was T, this was A, if this was my x of t, remember we got the transform of that? That was the first one we did? How many do? All right, what was that transform? Well, I'll tell you what, don't worry about putting it up here. You know there's a transform that we've worked out already. Isn't that right, class?
Yeah.
That was the first one. So let's assume we know that one. Now, the next thing you say, remember the building block approach, remember that. Now you're gonna say, I got something that looks like what? Is it going up or down?
Down.
Start at 0?
It starts at T.
What?
Starts at 2t over 3.
It starts at 2t over 3. Go ahead.
It goes down
Uh-huh.
till negative a, and then it goes.
Then
Well, no,
up.
no, sorry. It's away from the sawtooth down to negative a at t.
Wait. I don't-
It starts at the origin at a height of A and goes to that point you just.
At the origin?
No.
Do you want to see my book?
I offered to bring it up there.
Which one is it?
This one.
Oh, okay. And then, does it stay flat for a bit?
Yeah.
Yeah.
And then it goes down again?
Yeah.
Indeed.
And repeats itself? Well, it can't repeat itself, this is a Fourier transform. So, that's it, right?
Yeah.
Okay, what I'm gonna do with this one is how would you do this one? If there's a couple ways. If this is my x of t here, just leave it like that. I thought it was that waveform, but it's not, it's that waveform, which is the opposite one. How would you do this one? Just tell me. Guess.
Put it in negative t and shift it and then add the other thing.
Why don't we just take a derivative of this one? This one, I think it's quicker to take a derivative of. No, I'm serious, it is. All right, if you take a derivative, what do you get?
2 square pulse.
We got one impulse, square pulse. Another pulse, impulse, right? You all see that? Let's take a derivative of that. So if this is t, if I take a derivative of that, now I get this. Is that height a here? All right, if I take a derivative here, is this, that's 2/3.
Oh, it'd be t over 3.
What is this?
T over 3.
T over 3, thank you. And that's t over 2/3 t right here?
Yeah.
And that's t, okay. So here, it's gonna have a height of a, right, divided by cap t times 3. It stays there, shuts off here, I get an impulse that goes down to minus a, right? And then nothing, and then I got, hold it, this is negative, my bad. It should be negative here, and then back to 0. So this should be equal to minus 3a over t, then 0, then 0 here, and then back down to minus 3a over cap t, and then here, oh, by the way, this impulse is positive right here.
Yeah.
This is a positive impulse of a delta t, and then this will be also a positive impulse right here, where it's going to be a times delta of t minus cap t. All right, you can see how it happens. I've got a pulse function. I know the relationship. Agreed, class? It's shifted by what? T over 6, correct, class? So there's an e to the minus j omega t over 6. With this one, it's got a weight of minus 3a over t here, correct, class? Then I've got this impulse right at the origin. Well, it's just delta t, which goes to 1, so it simply goes to plus a, doesn't it, for the impulse? How many see that? Then I've got another pulse here, right? That's something we know, don't we, class? That's going to be another pulse function, correct? It's just going to be, it's really what? It's going to be, the width is t over 3, right? So it's t over 3, sinc of omega times t over 3 divided by 2, correct, class? Or omega t divided by 6. And then there's another phase shift of e to the minus j omega, how far? 5/6 of t, isn't it? Isn't that right, class? Because this is at 1/6, this is t, right? It's 5/6 there, right? Isn't that right? How many see this? It should be obvious how to do it. If you didn't see every detail, just realize you're just assembling the final product with known transform pair relationship. You know the pulse, you know what happens, the property of phase shifting, right? You know the delta function goes to just one, or it goes to the phase shift associated with the delta. And that's how you do that one. Now, I'm gonna ask you, do you have a specific question about the homework? I wanted to make sure I threw out some of those right off the bat, showing you how to assemble the answer based on basic functions or from a derivative approach. Any others? There's a couple of good ones in there. Remember, I gave you ones with cosines in there and e to the minus AT, didn't I?
Did you put the answers for the
Oh, yeah, you did. There was that giant chart you put up, and you said you put the answers, but you
I
didn't.
wanted you to work it, and you can get that. Those answers are where on Wolfram Alpha
Oh, yeah,
or what's that other one you're using? Symbol something or other?
Well, can we go over that chart real fast?
Which one? Just give me one.
So the x of t equals 2e to the negative 2t
Go ahead.
u of t.
Anybody want to help them out with this one? 2 over.
Oh wait, no. I thought like you have to do something with that. That's just a normal.
Can you plug that into the x of t cosine 5 of t?
Yeah, sure. I mean, if you take this times, we put 2e to the minus 2t times cosine of 5t, right? U of t, where does that go to? Well, come on. 2, right? I mean, you did it this way before. What did you do? You had a plus s over a plus s squared plus omega naught squared. Do you remember that? Remember? That was for what? Laplace, correct? With Fourier, what happens? I mean, sorry. Here, let me do it this way. We'll do it 2 ways. First is, do you all agree that's modulation? How many C? You got a cosine times a waveform, some x of t, correct? So what I can do is say this is my x of omega. Now I'm going to say this is 1/2, right? And then it's going to be this, 2 over 2 plus j, not of omega, but omega plus 5, correct? And then it's plus 2 over 2 plus j omega minus 5. Do you all agree with me there? It's modulation, isn't it, class? Now you can. That's the right answer, right? If you want to, you can get a common denominator, can't you? And go from there. That's fine. You can get a common denominator. You can actually group it, or you can actually take your Laplace transform for e to the minus at cosine omega naught t u of t, and you know that goes to what? A plus s, right? Over a plus s squared plus omega naught squared, right? And replace s with j omega. You'll get the same answer because it's only non-zero for t greater than 0. Follow me on this, class?
Would there be a 1/5 in front since it's 5t?
There's a 2 actually, right? Right?
What about the time scale because it's 5t? Do you have a 1/5 in the front?
What are you
Not
talking about?
modulation.
Oh,
This is modulation. This isn't scalar.
Wait, why would you have a 2?
Hold on, what?
Didn't we already put the 2 in when we the original?
Yeah, the 2s are.
Oh, you're right. My bad. You're right. I'm trying to get in a hurry here. Yes. Whoever had a question. Did you have one?
That's it.
All right. Sorry about that. All right, class. Let's go ahead and take care of this quiz. So do me a favor. Spread out. One desk between you and your neighbor that's empty. Nothing, no wearable electronics, no calculators, no phones. Take your phones out, put them on your desk upside down, and stand up when we come by. Appreciate it. I'm asking you to stand up to make sure there's nothing you're sitting on. Don't write on your hand. Spread out. Don't spread hands out.